we will now consider the six trig functions from a right triangle perspective. What I've drawn here is any right triangle. Notice the angle here, theta, is an acute angle between 0 degrees and 90 degrees. Therefore, if we're going to put it on the circle or on the coordinate plane, we'd say it lies in quadrant 1. Notice this doesn't necessarily have to be a unit circle. The hypotenuse here doesn't have to equal 1. From this angle's perspective, if we put our baby blue eyeballs looking through that angle, from this angle's perspective, the opposite side is found here, the adjacent side is found here, and always across from the 90-degree angle or the pi over 2 angle, the right angle is the hypotenuse. So we're talking about right triangles here. From this perspective, sine is opposite over hypotenuse. I'm going to write that as O over H. Ah, look what I get for free. Cosecant is hypotenuse over opposite, and you should notice that those are reciprocals. Cosine is adjacent over hypotenuse, which I'll write as A over H. Oh, look what I get for free. The reciprocal of cosine is secant, which is hypotenuse over adjacent. And you can see that these fractions have just been flipped. Denominator became numerator, numerator became denominator. Tangent, if we're following our SOHCAHTOA idea, is opposite over adjacent. Opposite over adjacent, which means cotangent is adjacent over opposite. And again, you'll see that these two are reciprocals as well. In this problem, we are asked to find the exact values of the six trig functions. Now, later we're going to talk about why they are in fact functions. So what we're going to do is, if we're asked about angle theta, we're going to put our nice baby blue eyeballs looking through this angle. So from this angle's perspective, the opposite side is 4 and the adjacent side is 3. So sine, SOHCAHTOA, we know sine is opposite over hypotenuse. Well, first things first, we have to find out what the hypotenuse is. Using the Pythagorean theorem, which says a squared plus b squared equals c squared. Now, what is A? A and B are the legs, the non-hypotenuse sides of a right triangle, and C is the hypotenuse. So if I do the math out, I'll have 3 squared plus 4 squared equals c squared. 3 squared is 9, plus 4 squared is 16, gives us 25 equals c squared, which implies that c is equal to plus or minus the square root of 25. But we're talking about the hypotenuse, and the hypotenuse is always positive. That's why I'm going to forget about the negative root and just deal with the principal or positive root, which is 5. So here, this side is 5. Sine is opposite over hypotenuse, or 4 over 5, which means cosecant is hypotenuse over opposite, 5 over 4. If you get this one correct, you'll get this one for free if you flip it, take the reciprocal. Cosine is adjacent over hypotenuse, 3 over 5. That means secant is hypotenuse over adjacent, and you can see that those are reciprocals as well. Tangent is opposite over adjacent. That's that TOA of SOHCAHTOA, which means cotangent is adjacent over opposite, 3 over 4, and you can see that these are reciprocals as well. We just figured out that if we have legs of a right triangle of side 3 and 4, if we apply the Pythagorean theorem, which says leg squared plus leg squared equals hypotenuse squared, we found out if we had 3, 4, we had 5. That was what we'd call a Pythagorean triple. It's one of the most famous ones. Now, if you Google Pythagorean triples, you'll find that we have endless amounts of Pythagorean triples. But here are some common ones. 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17, and 9, 40, 41. That's personally my favorite one there. You'd want to commit those to memory because they're just going to save you time in the long run. Otherwise, you'll have to do the Pythagorean theorem and do the math each time.